We have 3 pages of material to go through today, so we would like to introduce materials that explain the state of nuclear fuel in a reactor when the water injection system fails. With regards to the nuclear reactors, we are working to achieve a cold shutdown state by controlling the volume of water injection, in order afterward to keep those reactors isolated. Today, allow me to explain what will happen if the water injection is by chance disrupted. Basically, we have backup facilities for the feed water system such as spare pumps, emergency power source cars, and firefighting vehicles, so that we will be ready to restore the system immediately. Today we will introduce what will happen and how we should respond when the system does not function in spite of those backup facilities. As illustrated at the bottom of the slide, first let me explain some of the images depicting the state inside the reactor when the feed water system is disrupted. Given that this is just an image, please understand that this is just a rough depiction of the state at the bottom of the RPV. First, at present, the words normal time are displayed on the left-hand side. However, we estimate that the damaged fuels dropped down to the bottom of the RPV. At present, it is both through the water injected and the water leaking out through the bottom combined with its evaporation that we are able to remove the decay heat. Therefore, we presume that the current temperature and pressure level of the RPP are well balanced between the amount of water injection and the combined amount that is evaporating and leaking out. Please look at the illustration in the middle. If the water injection is disrupted under any circumstances, the water level will lower due to the shutdown of water supply. As a result, the amount of fuels exposed increases. Following this, we presume that the longer this state continues, as described on the right-hand side, the amount of water will almost reach zero, and the amount of exposed fuel will increase further, raising the fuel temperature. We will describe what we think occurs when the water injection system fails. In principle, we will continue the water injection sourced from the water tank via the use of a hose through the injection pump into the RPV. We think the possible reasons for the failure are as follows: pump trouble, problems at the system that supply electricity to the pump, damage to the feed water line that leads to water leakage, and as for the water tank, the loss of the water source that supplies water for injection. In case of failure, let me explain our response measures. First, when pump trouble occurs, we start up a standby pump or activate an emergency pump that has been installed on the upland grounds. Second, in the event of AC power loss, we will resume operations of the emergency pump that we have on the upland grounds or restart water injection by using a firefighting vehicle that doesn't require electricity. Upon the loss of the water source, we switch over from the buffer tank to the filtrate pump in order to resume the injection. Though we didn't put it here, we have another injection tank so that we can attempt a water injection just in case. If the feed water line was damaged, we resume water injection via a pump that is installed next to the pure water tank or via a hose that we have prepared for the accident along the regular line. As we have described so far, in the event of a single failure occurring, we are able to restart the injection within approximately 30 minutes. Relating to the evaluation of the reactor situation in the event that water injection is stopped, we assume that all of the decay heat contributes to the increasing fuel temperature based on the conservative evaluation of the condition that the reactor was in an adiabatic state. Actually, we expect that heat removal of the fuel will be achieved due to the evaporation of injected water since the water injection stopped as shown in slide 2. Meanwhile, this time we conducted an evaluation based on the condition that all heat released in the reactor contributes to increasing fuel temperature as soon as the water injection is disrupted. As for the evaluation results of the decay heat as of October 1st, Unit 1 was 64 megawatts, Unit 2 was 0.91 megawatts, and Unit 3 was 0.93 megawatts. Regarding the specific heat and weight of the fuel described in this table, if all decay heat contributed to the increasing reactor temperature, we conservatively expect that the appreciation ratio of fuel temperature is approximately 50 degrees Celsius per hour. To be precise, the ratio is approximately 48 degrees Celsius per hour for Unit 1, approximately 50 degrees Celsius per hour for Unit 2, and approximately 51 degrees Celsius per hour for Unit 3. Therefore, in case the water injection resumes approximately 30 minutes after the stop of water injection, we presume that the fuel temperature appreciation ratio will be approximately 25 degrees Celsius per hour, that is half of the above evaluation as shown in page 4. Although we explained that we will resume water injection approximately 30 minutes following the disruption of water injection, we additionally explained how we would respond in the event that multiple facilities were damaged as shown in page 6. We have to resume water injection by relocating fire trucks or hoses in the event of a tsunami hitting again due to a strong afterquake that destroyed multiple facilities. According to this flowchart, after the functions of the multiple facilities were lost, we relocated the fire trucks, confirmed the current situation of where the hoses had been laid out on the ground, and conducted an environmental survey. After that, we expect to restore the hoses and resume water injection to the reactor following equipment installation. We assume that these steps will take approximately 3 hours. Therefore, we assume that the fuel temperature will increase by approximately 150 degrees Celsius in the case of an approximate 3-hour water injection disruption. What will happen in this particular situation is shown on page 7. In case water injection is disrupted for a long time, we assume that the oxidative reaction of zirconium with water will escalate due to the appreciation of fuel temperature. Based on the assumption that the fuel temperature at the earlier stages was 300 degrees Celsius, it will take approximately 19 hours for Unit 1, approximately 18 hours for Unit 2, and approximately 18 hours for Unit 3 until the temperature reaches 1,200 degrees Celsius, where oxidative reaction of zirconium with water will escalate severely. Therefore, we have to resume water injection during the 3 hours since the water injection was disrupted. In this case, we have to inject a large volume of water in order to remove not only decay heat, but also reaction heat due to the oxidative reaction of zirconium with water, with a large volume of water injection through 2 lines connected to 2 fire trucks situated one behind the other as described in the above figure. Additionally, we evaluated that a significant volume of zirconium inside the reactor was already used at the accident on March 11th because this assumption concerning reaction time is that of the normal situation of the reactor. And we consider that the possibility of oxidative reaction of zirconium with water occurring is difficult if water injection is not being done. Therefore, we consider these assumptions to be on the conservative side. Page 8. We consider that the temperature will reach 2,200 degrees Celsius. The melting temperature of the eutectic mixture consists of uranium, zirconium, and oxygen. 38 hours after the water injection suspension if the temperature increases at the pace of 50 degrees Celsius per hour. Regarding the damaged fuel at the bottom of the RPV, we believe that it also contains the cladding tube that melted and rehardened. In other words, it is a eutectic mixture consisting of uranium, zirconium, and oxygen. It will take 38 hours until the temperature reaches 2,200 degrees Celsius and 50 hours to reach 2,800 degrees Celsius, the melting temperature of the uranium dioxide. Therefore, it is assumed that the damaged fuel will drop down to the PCV through the RPV after 38 hours in the case of an RPV meltdown. However, if the temperature becomes high, given the strong effects due to radiation, as it is not definite that the temperature appreciation rate will be lower than 50 degrees Celsius per hour, In other words, since the appreciation rate will slow down slightly, it will take some time for a fuel meltdown to occur. Fission products that are released into the environment are assumed to increase, considering that the evaporation amount of metallic cesium will increase under high temperatures. If water injection is stopped for a long time, the radiation dose can reach 10 millisieverts, the figure necessitating the need for evacuation at the site boundary. However, the melted fuel heat is considered to be removed through the concrete and will not melt continuously in the case where the melted fuel drops down to the bottom of the PCV. Actually, the decay heat of Unit 3 was approximately 0.93 megawatts. Therefore, we assume that the melted fuel will be cooled and settle at the bottom of the PCV, where it will eventually harden. We consider a detailed analysis to be essential. At last, page 9. Concerning the present nuclear reactor water injection system, as we will install backup facilities, etc., as well as conduct formatting, we are making preparations to be able to resume water injection within 30 minutes of a forecasted single failure occurring. Water zirconium reaction will occur at 1,200 degrees Celsius, 18 to 19 hours after the suspension of water injection, considering a temperature rise at the pace of 50 degrees Celsius per hour. Therefore, it is essential to restart water injection to the reactor within 18 hours. Water injection was suspended for the following duration per this accident, as shown at the bottom of page 7. Unit 1, 14 hours. Unit 2, 6 hours. Unit 3, 7 hours. Given its importance, we will continue to improve the reliability of the water injection system.